Good afternoon, I am Mr. Ish. I hope everyone's doing well. Thank you for joining me for this video where we are looking here at a introduction to this concept of directional derivatives. I'm abbreviating as DD. Consider these 2 points over here before we get into the crux of this topic. Directional derivatives at a particular point is always a function of a certain angle theta. 2 different concepts which are coming into play. You have something in a particular direction and you have something with regards to a rate of change. Look here at this point too. Directional derivative gives the rate of change of a particular system or z. I'll talk about the z momentarily. At a particular point and in a particular direction. Look here at this equation. We're not worrying about the derivation of this. It's not in the scope of the video, nor is it in the scope of calculus, basic calculus. Look, dz over ds, derivative with respect to the z and the s variable is equal to a certain partial derivative with respect to the x variable, cosine theta, plus partial derivative with respect to the y variable and sine theta. These items are in a multiplicative format or they're in a product form. These are in a product. There's a plus in between. You're seeing here a total derivative taking a sum of partial derivatives. Now look, there's a z showing up over here. What does that mean? We're looking at items or systems which involve x, y's and z's. You'll have a z is equal to a format of an equation, and that equation will have x and the y variable in it. And that's what we're talking about here. A certain system, if you're talking about real life phenomenon, or a certain function or equation which is referring to a z equals format. Let's look over here at a basic example and then let's go from there. This right here is our template we have to utilize. We have an example over here. We have to find the directional derivative of this particular system or equation at a particular point 3, 1 at a particular angle in radians pi over 3. If you have this particular function and you were to graph it out, it would look like a paraboloid. You can look at it on online software tools, 3-dimensional graphing, x, y, z axis. You will have here a paraboloid. At a particular point 3, 1, this is your x and y value at a particular direction. From there, what is the derivative at that particular area? That's what you're looking at over here. These are directional derivatives. You would have to determine the partial derivative with respect to the x and the y variable, and you have the angle already provided. You have the point. How do you go about starting with these? You want to start here with the determination of your partial derivative x, and we can. When you're doing a partial derivative of this particular equation, you're looking at the x as your variable of interest. Everything else is a constant. From x squared, I'll get a 2x. From xy, y is a constant. It'll be y, because the derivative of x will be a 1. You have that done. Now let's look at this next partial derivative with respect to the y variable. Same equation. Treat the y as your variable of interest. X is your constant. This is a constant. It's a 0. Just like here when you're doing the partial derivative with respect to x, this is zeroed out because it's a constant. When you're looking over here, you have x as your constant, y as your variable of interest. You will have generated from here an x. Then from here, y squared, you'll have a 2y. Now things are taking form. We will bring everything here into this format. And I'm just moving this over here just for some space. This is what I have, and I'll erase this from right here. Let's bring everything here to determine our directional derivative. This right here is our directional derivative. It will give us a directional derivative for this function at that particular point, at that particular direction from that point. Bring the items in. I have 2x plus y. Then I have cosine of a certain angle, pi over 3. What's cosine of pi over 3? It's 1 over 2. Think about your trigonometric ratios. Then I have this item coming in here, x plus 2y. And then I have sine of pi over 3. You know from your trigonometric ratios, it's a root 3 over 2. That's what I have. Now what we have to do is plug in our values for x and y. I have x 3, y is a 1. I have a 3 times 2 is a 6 plus 1, which is a 7 times 1 over 2 is a 7 over 2 plus x and y is 3 and 1s. 3 plus 2, which is a 5 times root 3, 5 root 3 over 2. Bring these under a common denominator. I have a 7 plus 5 root 3, and this right here is my answer. What does this answer represent? It's a derivative answer. At a particular point, at a particular angle, we have a rate of change, and it's equal to that 7 plus 5 root 3 over 2, and you would know that to represent a slope of a particular tangent at a particular point for a particular system in a particular direction. This right here would be the slope of that tangent. 7 plus 5 root 3 over 2, it would be correct. And this directional derivative question comes to an end. Let's look over here at this other example. We have a particular equation here. Z is equal to y, e exponent x. I have a z variable, y, and an x variable. We have a particular point is 0, 3. You know that to be x and y, and a certain angle 30 degrees. You know that to be pi over 6. Now we have to bring everything here into this equation form because we're determining the directional derivative of this system at this particular point in this particular direction. How do we do it? Start by determining your partial derivatives. Your partial derivative with respect to your z and x variable using this is what? Your x is your variable interest, y becomes a constant. These are in products, so it's easy. You have a constant with a function with your variable of interest. The partial derivative here will be just y e to the x. Think about it, it's easy. Now your partial derivative with respect to your y variable is what? Here you're looking at a constant which is a product to your variable. This right here, in terms of this, would be no different than you saying you have a e to the x which is sitting outside. Now you're doing the derivative of y, which is just a 1, and your end result here will be just e to the x. Remember, when you're doing partial derivatives, one variable becomes a constant, the other variable becomes differentiated, and that's what we're doing. Y e to the x, for this particular part right here, this is my variable of interest, y is a constant, y e to the x, because the derivative of e to the x is e to the x. When I'm looking over here, the y derivative is a 1, the constant remains, and it shows through. Bring everything here into the format 0, 3 and pi over 6. This is equal to, I have y e to the x times cosine of pi over 6. What's cosine of 30 degrees? Think your trigonometric ratios. Here's 30, it opposes a 1, here's a 2, root 3. Cosine of a 30 is a root 3 over 2 plus I have e to the x, which is coming from this part of the equation. Sine of 30 degrees or pi over 6 is 1 over 2. Bring everything here into completion by plugging in zeros and threes. 0 is x and 3 is a y. I have 3 e to the power of 0, which is a 3 root 3 over 2 plus 0 and 3. E to the power of 0 is a 1, which is a 1 over 2. Combine it, you have a 3 root 3 plus 1 over 2, and this right here will represent your directional derivative for this system at a particular point in that direction 30 degrees. And it will be correct. Let's look here at one more question for this particular video. Let's spice things up just a little bit with this type of question. We're looking here at an electric potential question. You know the symbol for electric potential is a V. We have here an electric potential at a particular point on an x and y axis, x comma y. It is given by this equation here, V, electric potential is equal to natural log square root of x squared plus y squared. All of that is in the square root. We have to find the rate of change, which is in essence your directional derivative at a particular point 3, 4 in the direction of 2, 6. It is no different other than it being disguised in terms of a physics problem. That's all what it is. You can think of V as being a Z, then you're looking about at X, Y, and Z axis, or just keep it as is, V is equal to natural log, and you're looking here and worrying only about two variables. But in the end, our equation is still the same. Except instead of we're looking at Z's, now we're saying we have a dV over ds is equal to, I will have over here, your partial derivative with respect to your V and your X variable, cosine theta, and then your partial derivative V with respect to your Y variable, sine theta. Consider this, when you're looking over here, you're seeing it the derivative terminology. When you're looking over here, you're seeing partial derivative terminology, but that's fine. That's how the procedure is. The challenge over here is to determine the direction given the coordinates, but it is also to determine these partial derivatives. I'm going to erase this simply for the purpose of space. You've seen it. This right here is our format. It should be correct. We will plug everything in here accordingly as we determine it. Let's start here with the determination of the angle. I have something here on an x and y axis for the purposes of this video. I have 1, 2, 3, 1, 2, 3, 4, and it's 3, 4. Then it's going in the direction of 2, 6. And we can up this up some more. We're looking at 2. We have something which is going in this direction from 3, 4 to 2, 6. How will we determine the angle? Well, you could easily, you know, this right here is a 3, this right here is a 2. You can easily generate a right triangle, and when I do so and I make it slightly exaggerated, I'm looking 1 across, then I'm looking here 3, 4 to 2, 6. It's going 2 above, and you know here this will be a root 5. Your angle over here will be what? You can always think of this specific item here. Tan theta is always equal to a slope. You can do that. Slope is equal to a y2 minus y1 divided by x2 minus x1. My tan theta here, which is I'm interested in the theta angle is what I'm interested in, is equal to y2 minus y1. I have a 6 minus 4 divided by 2 minus 3. What do I have? 6 minus 4 divided by 2 minus 3 is going to be a 2 over a minus 1, which is a minus 2. When you do this and you start bringing in items, you're looking over here at sine theta based on this is equal to what? A 2 over root 5. And you're seeing here cosine theta is equal to a 1 over root 5. But what was the purpose of doing this part right over here? The purpose of doing this part right here, and don't get confused particularly over here, you're looking over here at this little negative right over here. There's a negative which is popping up, and that negative cannot be ignored. That negative is indicating you that you're looking here at a second quadrant angle. And because we're looking here at a second quadrant angle, you know in the second quadrant cosine is a negative, sine is a positive. Now this will be confusing for some students, and I'll clarify it for you. This right here was just for me to develop my right triangle, but it does not define anything with regards to the quadrants we're dealing with. What defines the quadrants we're dealing with is this negative sign over here and this particular fact. So when I'm looking over here at this triangle, which is like this, I can draw from this particular point over here a certain x and y axis, and it becomes like this. Then with regards to this, I'm looking at a certain deviation from my y axis, because this is representing that right here, and I'm using that to determine the fact that I'm here in quadrant number 2. Hence I'm determining here a negative in terms of a tan. You know in quadrant number 2 tan is negative, as it would be in quadrant number 4. From this specific representation right here, this becomes my origin right here, from which I draw a x and y axis, and I'm finding myself in the top left aspect of this x and y axis, 1, 2, 3, 4, and I find myself over here where I know cosine is negative, sine is positive, and these are my values. So let's put them down and then let's proceed with this question. I have over here sine, which will be a 2 over root 5. I have here a cosine, which will be a minus 1 over root 5. And let's get on with this question. What we have to do now that we've determined these directions, sine and cosine, it's over here. Let's do the partial derivative determination with respect to the x and the y. The function natural log square root x squared plus y squared, or your equation. Let's do it. You have to do chain rule and substitutions. If u is equal to x squared plus y squared but in a square root, then I have a function with regards to u which is ln u. If v is equal to x squared plus y squared, then a function with regards to v is equal to root v. Bring this into your chain rule. I'll do d over du. I have ln u. Then I'll do du over dv. This right here is a u. I'll have here a root v. Now do partial derivative v with respect to partial derivative x, because now I'm focusing on the x as we have to do the y as well. When I'm looking at this x squared plus y squared, if I do the partial derivative calculation, the y becomes a constant, it goes away. The partial derivative of x squared is a 2x. I bring everything in. I have a 2x. The derivative of ln u is a 1 over u, which is this. The derivative of root v is a 2 root v. The 2's cancel out. I have a x divided by u, which you know to be a square root of x squared plus y squared, and then I have a root v, which is a square root of x squared plus y squared. Look at that denominator, it's easy. The radicals will go away, the square roots will go away. You'll be left over here with just x divided by x squared plus y squared. This right here will be equal to partial derivative v with respect to partial derivative x. If you can imagine exactly from this equation what will be for the y, it will be exactly what you think, y divided by x squared plus y squared, because the procedure is the same. In that you're choosing x as your constant and the y as your variable interest. You end up seeing this. With respect to the y variable partial derivative, you'll have here a y over x squared plus y squared, because everything else stays the same. Now we just bring everything here into our ultimate equation and we're done. What is my equation? It's this. The potential with regards to the derivative is equal to, you have x's and y's coming in through with the point at 3 comma 4. I have x divided by x squared plus y squared, 3 comma 4. It'll be 3 over x squared plus y squared will be what? 9 plus 16. It'll be a 25. You know it's a cosine theta, which here is a minus 1 over root 5 plus. Now I'm going to do y over x squared plus y squared. The 25 will stay the same because we've determined that. But y here is equal to 4 over 25. And then a sine theta, which will be here a 2 over root 5. Combine all of these, what do you have? You will have a minus 3 plus 8 over 25 root 5. You can simplify this. It'll be a 5 over 25 root 5. You can even simplify this further. 5 will cancel out with that 25. You'll have a 1 over 5 root 5. So let's simplify this. I'll have here a 1 over 5 root 5. Now if you wanted to rationalize this denominator, you can. We may end up going back in loops somewhere, but we can rationalize it. I'll have here root 5 divided by a 25. What does this represent right here? This right here is our rate of change, or my directional derivative for this particular system, which is representing a certain electric potential at a particular point in a particular direction. It should be correct. And with that, our video comes to an end. Thank you for watching.